Hey guys, I'm just doing a quick follow-up video on my last video about tuning systems. I figured we could take a look at some different tunings of major thirds. What I've done here is I've set up a few oscilloscopes. Basically, they're devices that you use to look at waveforms, sound waveforms. And what we're going to do is we're going to use them as kind of a visual to kind of help hear what's happening. So if you look here, I have a composite, sample 1 and 2. So this is actually the sound you're hearing put together. This is sample 1, so this will be one waveform. Sample 2 down here, another waveform. I've also set up a X and Y composite of samples 1 and 2. Basically, it's just a two-dimensional kind of drawing of what the sound's going to sound like. If you haven't watched the last video, I definitely recommend checking it out because it talks a little bit more about the different styles of tuning and where these tunings come from. And today we're just going to actually hear some of it. So I'm going to start off with the visual element because sine waves can be very tiring on the ears. So we'll just start off just looking at it. So this is an example of a sine wave right here. It's very kind of smooth. It's one of those perfect kind of waves. It's the closest to perfect sound. It doesn't have any overtones. And here is a justly tuned major third. Now, if you notice on the composite, there's a very consistent shape to the composite sound. It's very even. The sound's not wobbling around or beating. I'll talk about what that means in a second. And you have this X and Y composite over here on the top right. And that X and Y composite, the sound looks very pure. It's staying pretty consistent. I'm going to go ahead and do a stereo spread. So the sample 1's going to be on your left speaker, and sample 1's going to be on your right speaker. And I'm going to do a mono with zero spread, so both samples are going to play together. So as you can hear, it's very pure tone. It kind of grates on your nerves a little bit because it's so pure. But now we're going to change the sample. I'm going to play it again, and then I'm going to switch to an equal temperament. And you're going to see the sound waves change. It's going to speed up just a little bit on sample 2. And also you're going to see this perfect oscilloscope on the top right start to wobble and move around. It's not going to stay uniform anymore because it's not that perfect 5:4 ratio. So I'm going to play the sound first, and then we're going to hear the shift. And to Pythagorean. And as mono. So what you're seeing here, the fact that you're seeing all this really inconsistent waves moving around kind of chaotically. Unfortunately, these waves kind of slow down a little bit on my computer when I'm recording video of the screen and of myself at the same time, as well as recording the audio. But you can see that they're not nearly as pure. And what's happening is the sound's beating against each other. And to demonstrate this beating, and you can actually hear a rhythmic pulse in the sound waves themselves, I'm going to play a justly tuned E right here and a equal temperament E. And we're going to listen to how you see this top composite, how it's shrinking down really small and then getting large. That's because of the sounds waves are moving in and out of phase. So they're canceling each other out, and then they're causing each other to spike. All right, so here is a mono example of that. And that pulse you hear is what we call beating. Now here is an example of Phrygian, or Pythagorean tuned E. As you can hear with the it's a much faster rate, meaning that the two tunings are more out of tune than each other. So the slower the wobble, the more in tune the sound is. The faster the wobble, the more out of tune the sound is, or the pitch is. So now I kind of want to demonstrate a few of the mean tone temperaments and Pythagorean temperaments, some of those audio files. We're going to start with the quarter comma wolfs. So we talked about the wolf tones, how some of the perfect fifths are a little bit out of tune using the quarter comma system. I played some samples and tuned some stuff up digitally, and now we can kind of hear what those sound like. Yeah, as you can hear, the last perfect fifth is really out of tune. You can actually hear some of that beating, that kind of wobbliness that we talked about in when we were just listening to sine waves. Now I want to also play you a couple things. I'm going to play an example of a diatonic mean tone temperament and a diatonic equal tone temperament. And they're going to sound fairly similar, but I want to demonstrate just kind of their very subtle differences. And like I said, if you play these two samples at the same time, they're going to really, you're going to really hear how out of tune they are. And that's equal temperament. That's the temperament we normally use, just in a C major scale. This is a quarter comma mean tone diatonic. As you can hear, some of the tunings are a little bit different, but it's very subtle. It's definitely one of those things that if two people were playing in two different temperaments, it would really stand out. Where things get really different is when we start to do chromatic tunings. So here's an equal temperament chromatic tuning. Alright, so that's just chromatic scale. All the black and white notes on the piano in equal temperament. And here's a quarter comma mean tone chromatic scale. Yeah, it's very subtle. I'm gonna also play a sample at the end of this video of those two together, and you'll be able to hear the differences. Here's a Pythagorean chromatic scale as well. They kind of cheated a little bit on this one because with Pythagorean tuning you get differences between D sharp and E flat, so all the enharmonic notes, all the black notes on the piano can be tuned slightly different. So I think this one they used the average of the two. Yeah, you can hear that one's a little bit off. I want to play that one again. Hopefully that helped. Thank you guys for watching. There's a lot of resources on tuning system. A lot of the times they get into really complex mathematics because they can get really kind of they can get crazy really fast. But hopefully this video kind of helped allow you to kind of hear some of these differences, and hopefully the last video helped on kind of understanding how these kind of different tuning methods arrived. All right, have a great day.